All right, in the last section here, what we're going to talk about is how we're actually going to build these trees. And what we're going to use and build upon is this idea of parsimony. And what this is the maximum likelihood that two events are related to one another. That's, or the most probable outcome is what, parsimony is describing. So we're going to look at the trees that we're making and make sure that they're consistent with the facts that we've got. And over time, this tree should represent the likely sequence of events that have occurred throughout evolutionary time. And as more evidence becomes available, we might have to modify the tree. But again, it's just built on this most probable set of outcomes. So if we look at the example that we talked about earlier in that a human, a mushroom, and a tulip, which ones are most closely related? We probably agreed that the mushroom and the tulip seem like they're the most closely related. But as we start looking at this molecular data, we start to see that the human and the mushroom have a 30% difference in their DNA, whereas the human and the tulip have a 40% difference, as do the mushroom and the tulip. Okay, so we have to look at the most parsimonious type of tree. So we've got two trees down below here, and you can see tree 1 is more likely than tree 2, and we'll just kind of explain why here in a second. But what we see from this is that the mushroom and the human are the most closely related, and the tulip is not as related to either of those two, the mushroom and the human, as the mushroom and the human are to one another. Okay, so if we're looking at these different types of trees, what we can see is that when we're looking at the differences between the human and the tulip, we say that there's a 40% difference in the DNA, while we have the 5 and the 15 is 20, and 20, there's our 40% difference. Tree 2 would be 15 and 25, which would also add to 40, but what it's saying is that the evolution in the human lineage would slow down in comparison to that of the tulip, and that's not really the most parsimonious outcome. That's why we say that tree 1 is more likely. Okay, and here's the explanation that kind of talks about tree 1 being the most parsimonious or most likely, comparing those two together. Okay, if we look at the mushroom now and the tulip here, again, we've got 5 in 15, okay, is 20, and 20 is 40, and that's more likely than saying 5 and 10 is, or 5 plus 10 is 15 plus 25 is 40, because what we're saying is that the mushroom lineage slowed down as compared to the tulip lineage, and this is less likely. It doesn't mean it doesn't or didn't happen, but it's not as likely of an outcome. And again, this is the explanation for tree 1 becoming being more parsimonious, because we have to assume that they're evolving at the same rate. Okay, so throughout much of evolutionary history of a particular organism, what we can look at are different types of differences within the genome. And different genes evolve perhaps at different rates, okay, within the same evolutionary lineage. And these molecular trees have the ability to kind of encompass both short and long-term periods of time because of the genes evolving at different types of rates. So we can assume that the genes are going to evolve at, or the genomes, excuse me, are going to evolve at a constant rate relative to the other ones, but particular genes within them may in fact involve evolution at a different rate. So you have to take in all of these factors into account when you're building up these trees. So if we look at ribosome encoding DNA, this evolves very slowly. Ribosomal RNA and the genes that code for it evolve very slowly because they're very, very important, and any changes are likely weeded out of the population because they're not going to improve the genome, or the organisms that have them really in any different way. So we can look at ribosomal RNA as being something that can take us way back in time, because the organisms that have these diverged, many millions of years ago, and the genes within the two different lineages evolve very slowly. So it's a good way to date things that are very old. Whereas mitochondrial DNA evolves very quickly, and this can be used to show more recent evolutionary types of effects. Okay, so when we're kind of developing these things and looking at them, we can build from the different evolutionary rates these molecular clocks, and this can help us make an estimate for how long ago a particular organism evolved from a common ancestor. And what this is going to measure is really the absolute time of this evolutionary change, and it gives us a good basis for evolution based on these genomes evolving at a seemingly constant rate of time. And certainly it isn't always going to happen, but again, it gives you a good starting point. And the main assumptions of a molecular clock are that when you're looking at the substitutions that occur within genes that have evolved from a branching ancestor, in other words, these orthologous genes, you have a common ancestor and then you have a branch. And what you're saying is the changes or the substitutions that occurred in lineage 1 and 2 are going to be proportional to one another. Okay, and when you're looking at paralogous genes now, these are genes that you have a particular organism that kind of goes through time, and then as time passes on, you're going to have these gene duplications that are going to occur, and these are going to occur in a proportional amount. So it's going to give you a kind of a reference in making an assumption that these changes that you're seeing are occurring in proportion to one another. And I wouldn't be too concerned with what orthologous and paralogous means, but it's two general classifications. One, orthologous, is based on branching evolution, whereas paralogous just shows changes in the organisms that occur through time. So one and the ancestral organism might be a little different than the particular organism that we're talking about now. But again, it's just nothing super important for you to remember. Now, if we're looking at this molecular clock now, as long as we have a reliable rate of evolution, we can calibrate that clock by graphing different nucleotide differences against the times in a series of different changes that have occurred and changes that we know have occurred based on some of the information that we have, for instance, like from the fossil record. Okay, and we can create this line which allows us to draw a line of best fit based on the data that we have, and then we can look at the number of mutations that have occurred, the divergence that has occurred through time, and kind of allow us to piece together some of these evolutionary events and give us a better picture and maybe guide us in the right direction of where to go to look at the evolutionary relatedness of these particular types of organisms. So for instance, if we look here, we can take some of geological data and we can use it with some of this other types of data to kind of develop these branching diagrams and explain how this branching evolution has occurred. So if we look at these different types of organisms that live on the Galapagos Islands here, and these are different types of fruit flies. For instance, based on the molecular clock data, what we've done is we've looked at a particular organism on Maui, and we can see that it's believed that these things split somewhere around 500,000 years ago if we draw our line there. And if we look at the geology or the geological data, we can see that the new island of Hawaii has been in existence for about 500,000 years. So this branch point here is showing us it occurred about 500,000 years ago based on the geologic data and what this molecular clock data is telling us. Same thing for this organism that split from Oahu and Maui. This looks like, if we draw our line down, it's about 1.5 million years, and we can say that the island came into existence about 1.5 million years ago. And then same thing with the one on Oahu here. We can say that this occurred about 3.8 million years ago. Well, right here, Oahu came into existence then. So what we're going to use is multiple pieces of data, and this is just an example to show you how geological data, molecular clock data, how these different types of things can be used to develop this particular type of tree, geological tree phylogenetic tree here based on the geological data and the molecular clock data. So you can use all different sorts of pieces of information to kind of piece this data together. Okay, so now with the molecular clock, although the idea of the molecular clock can be used to estimate the genes, the ages of them, the behavior of them, and so forth, some of these things do evolve at different rates, and it makes these estimation types of things difficult. But the point is that it gives us a good kind of basis or starting spot to kind of go from, and then kind of build from there and piece together all of the data that we have to kind of make sense of all this. Okay, so Some of the reasons why these molecular clocks aren't entirely accurate is because sometimes these nucleotide sequences change at different rates. Sometimes they change at constant rates. Sometimes the effects are neutral. Sometimes they're not. So just, again, looking at the differences in DNA can tell us sometimes the information is fitting in with the other known data that we have, and sometimes it's not. And then some of the differences in the DNA can make really looking at the evolution of this DNA difficult, and it makes dating the fossils very difficult as well. So there's lots of different reasons for this. But again, as we said, it serves as a good starting point for us to kind of launch further research and get more data and go from there. Okay, so that concludes chapter 26. And again, make sure, as always, you got any questions, you write them down, and we'll talk to you soon.